Welcome to this video lecture on types of heat transfer and the first law of thermodynamics without mass flow. If you look at your screen, you'll see a picture of a heat sink on a microprocessor. So this structure here where you have these vertical metal fins on top of this base plate, this is mounted on top of typically like a CPU or GPU that's underneath it. And the purpose of it is to transfer heat from the CPU or GPU. So modern CPUs, for example, cram a lot of electronics into a very small density. It's a very small space, so it has a very high density of electronics in a small region. And these electronics aren't 100% efficient, so they generate some excess heat. In order for those electronics to function properly, they need to remove that heat. And since there's a lot of energy being created in a small space, typically what one has to do is to mount some sort of heat sink attached to it, or some way to remove that heat into the surroundings. And so a heat sink like this is pretty typical. The heat sink operates via conduction, so what will happen is let me see if I can sketch this out here. The microprocessor from below will generate some heat that then moves into the metal of this heat sink, and then that heat is conducted up through these fins, and then air blows past and removes that energy via heat transfer through a mechanism called convection. We'll talk about that a bit later. But without these kinds of heat sinks or heat removal techniques, modern microprocessors wouldn't function very well. In fact, it's one of the big areas of research, and Purdue's actually involved in a lot of that research through an organization called the Cooling Technologies Research Center, so CTRC. Anyway, I thought that was kind of an interesting application of some of the things we're going to talk about today. So let's go ahead and get into it. First thing we're going to do is talk about types of heat transfer. Now, for this particular course in thermodynamics, you don't need to know all the different modes of heat transfer and how to model them. That's saved for a different course. In the Purdue curriculum, it's ME 315, which is heat and mass transfer. That's a course you'd take typically the second semester junior year. At this point, all we need to know is that we can exchange energy via heat transfer. But I'm going to give you just a little more information about it, just for your own reference. So there are three types of heat transfer: conduction, convection, and radiation, and they're all illustrated in this picture here. Conduction is the transfer of energy from more energetic particles of a substance to the adjacent, less energetic ones due to the interaction between particles. So imagine you have molecules in some kind of solid material. They're vibrating, right? So that's what gives them some temperature. They're vibrating. But if one molecule is vibrating a lot more, so it has a higher temperature, it bumps into the neighboring molecule and causes it to vibrate, and so it raises its temperature. So it's that vibration and kind of bumping into the neighbors that causes heat or energy, really thermal energy, to move from one location to another, from a higher temperature to a lower temperature, and that's what we call conduction. Just like in that heat sink, when you go from the microprocessor up into the metal structure, that's the process of conduction. Convection is energy transfer between a solid surface and an adjacent fluid, like a liquid or a gas. Remember, a liquid or a gas, they're both considered fluids. So it's energy transfer from a surface to an adjacent fluid that's in motion. And it involves the combined effects of conduction and what's known as advection. So conduction, again, you're getting the molecules in the solid surface bumping into the molecules of the fluid, so there's some energy transfer there. But advection is the movement of the fluid. It's just carrying those molecules away and replacing new, colder molecules adjacent to the solid surface. So convection would be like, let me see if I can draw the picture down here. So here's the solid surface, and then here's the fluid passing by. So again, you have these molecules bouncing around in the solid surface, and then they conduct some energy into the fluid. So there's the conduction part, and the advection part is the movement of that fluid being carried away. So those two processes combined together is convection. In fact, the name convection is a combination of conduction and advection, convection. So these are the two very common types of heat transfer that one sees just in everyday engineering practice. They both can be quite important in practice. So convection is the process where if you have air blowing past the fins of this heat sink, then it's carrying that energy away. So typically you'll have a fan inside your computer or whatever to blow air past these heat sinks. So it's relying on convection to remove the heat. So conduction to get it from the microprocessor into the heat sink, and convection to move air past the heat sink to carry away the energy into the surroundings. Now the third type of heat transfer is radiation. Radiation is the energy emitted by matter in the form of electromagnetic waves, and we'll just leave it at that at this point. Unlike convection and conduction, radiation doesn't rely on some interstitial medium. So with conduction, you need to have matter that vibrates against neighboring parts of matter. With convection, you need that same sort of conduction plus a fluid to carry it away. So you need some sort of matter to help with the heat transfer. Radiation doesn't require that. You can have radiation from an object in a perfect vacuum, for example. So it's a transfer of energy through electromagnetic radiation. And that tends to become very important when you deal with high temperature applications. Okay, so it's still a mode of heat transfer that's always occurring, but it's often most important when you deal with really high temperatures. So the picture that we have on the screen here shows the different types of heat transfer involved in like heating a pot of water. So conduction would be when the pan gets hot, it's conducting heat through the handle. Might get this person's hand really hot, so it's just the conduction through the metal. Convection is occurring inside the liquid here as the cooler liquid on top starts to settle, and then it picks up energy from the bottom of the pan, and then it kind of cycles around, so you're getting this advection combined with conduction at the bottom of the pan. And then the radiation is the infrared radiation, for example, here, that's the energy being emitted by the fire that you feel warmth, and that would happen even if you were in a vacuum, you'd feel that warmth. So that's radiation. Now, like I mentioned before, in this course, you don't have to worry about all the different modes of heat transfer and how you would model those. That's for a different course. All we care about here is that we can transfer energy via heat transfer in some way. Using one of these three methods, we don't have to identify which one. We just know that energy is being transferred. So a few notes. The convention is that a positive Q, so we'll use the symbol Q for heat transfer. So and that, by the way, has dimensions of energy. So it would be like units of joules, for example. So heat transfer is positive, meaning that energy goes into our system. So if I draw a picture of a system here, so this is our system. So a positive Q means that energy is going into our system via heat transfer. And if it was negative, it means that energy would be coming out of our system via heat transfer. That's just the standard convention. Again, I typically like to put in the subscript into or out of, just to make it absolutely clear. So when I write out the first law, I'll put that subscript Q into, for example, just so I know that which direction I'm assuming the heat transfer is going. Okay. Like work, heat is not a property. It's just an energy transfer process. So it's not a property like temperature or pressure or internal energy. It's an exchange of energy. And so it's path dependent. Just like work was path dependent, I talked about that in a different video lecture, heat is also path dependent. So when we write out the first law, for example, I'll write it in differential form here. So here's the first law written in a differential form. When I say differential form, I mean just in terms of little bits. Here is the small change in the total energy of our system. So here's our system. And that's equal to the little bit of heat, or a little bit of energy I've added into the system via heat transfer. And again, I use the little delta rather than a D to indicate that it's path dependent, just like what I did in a previous lecture on work, minus the little bit of work done by the system on the surroundings. And again, that one is also path dependent. So if I sketch the work term here, that would look like this. Okay, so we've talked about the first law before in a different lecture, but here it is again, just written in a differential form in terms of little bits. Okay, the third item here is Q dot is the rate at which energy is transferred via heat transfer. So we can talk, so Q here would just be the total amount of energy transferred in terms of joules. Q dot is the rate at which that energy is transferred. So that would be joules per unit time, like joules per second, and that has the units of watts. Okay, so typical unit here might be watts. Lastly, adiabatic, that's a term we'll use frequently when we're referring to heat transfer. And what adiabatic means is that there is no heat transfer, that Q dot or Q are equal to 0. That typically we assume things are adiabatic if the container or the system is well insulated, for example, so that there's still some heat transfer going on, but it's small. And so as an engineering approximation, we'll just assume that it's negligible. So we'll assume that process is adiabatic, in which case the Q term would be 0. Okay, so that's really all you need to know about heat transfer. We're not going to get in much more detail other than that. We'll be dealing with, like work, we'll be dealing with heat transfer quite a bit in the course in our analysis using the first law of thermodynamics as well as the second law of thermodynamics. So speaking of the first law, let's go ahead and spend a little more time talking about it. So you've seen the first law of thermodynamics before in a prior lecture. I'll just talk here specifically about the first law of thermodynamics without mass transfer. So one way we can write the first law is in this form. This is the form for a system. Remember that a system is a particular quantity of matter chosen for study, so there is no mass transfer in a system. It's always the same mass, right? So when we write out the first law of thermodynamics without mass transfer, it's that form. There's just no, we don't have to worry about mass transfer because it's always the same mass. So I'll just repeat the picture I had on the previous page. So here's the Q into the system. Here's the work done by the system. And this again is the change in total energy of the system. And that total energy can include changes in the internal energy. In an upcoming lecture, we're going to talk more about how we find changes in internal energy, how we actually determine that property. This is a property of the system. So in addition to changes in internal energy, we have changes in kinetic energy of the system. So you already know how to calculate kinetic energy. And we also have changes in potential energy of the system. So a change in total energy of the system includes those changes in those three types of energies. Okay, so that's this term on the left-hand side. This, of course, is the heat. Well, it's the energy added into the system via heat transfer. And then this one we've talked before. This is the work done by the system on the surroundings. And that's also a form of energy transfer. So heat transfer and work are both ways of exchanging energy between the system and the surroundings. And since here we're adding energy into the system, so a positive Q will result in a positive change in the total energy of the system. Here the work is leaving the system, so that means energy is leaving the system, so that we have a negative, which would decrease the total energy in the system. So this is a form that we'll use very often when we deal with systems or control volumes without any exchange of mass. Okay. Now here's another form that's written in a rate form. This is the control volume form. All it is the same equation, but I've just taken a time derivative of it. So instead of a change in total energy, we have the time rate of change of total energy. Instead of heat transfer, we have the rate of heat transfer. Instead of work, we have power, or the rate at which work is being done. And then we have these additional terms. I've talked about these before in a different lecture. These involve, so here's a control volume. These involve places where you have some mass transfer in and out of the control volume. So as mass comes into the control volume, it carries some of its own total energy with it. Here it's written in terms of specific total energy. So the total energy that this incoming mass brings in is m dot times little e. And so that's into the control volume, so that adds in some energy, that increases the total energy of the control volume. and then this mass is going out, so those little bits of mass take their internal or their total energy with them and take it out, and so that decreases the total energy of our system. But if we're dealing with a system, if we're dealing with the first law without mass transfer, then these terms just go to zero. There is no mass transfer because we're specifically looking at a case without mass transfer. And so then what you're left with is just this expression, which is precisely the same as this one, except it's just written in terms of rates rather than changes. So this is the change in total energy. This is the rate of change of total energy. Okay, so this is like taking the time derivative of this equation here. So we can use either form, this one or this one. It just depends on whether you're interested in the rates of change or if you just want to know the total change in total energy, for example. Okay, so a few notes here. Just a reminder that the total energy of the system includes the internal energy, kinetic energy, and potential energy. The work done by the system, we've talked about this in a prior lecture, that can include things like pressure work or PDV work or moving boundary work, whatever you want to call it. It can also include shaft work, spring work, electrical work. Maybe there's some other kinds of work we haven't talked about, but remember, it can be comprised of different types of work. The third item here are common modeling assumptions. So when we start to work problems involving the first law, we often need to make certain assumptions as we solve that first law relation. One common one is an adiabatic process. I just talked about this. That means that the heat transfer term is zero, and that might occur if you're dealing, for example, with a well-insulated container, where the heat transfer effects, maybe they're really there in reality, they're just very small. And so we make the engineering approximation that we'll just neglect it entirely. Another one might be there's no pressure work, which means that the work done by pressure would be zero. An example of that might be if you're dealing with a rigid container. Remember that pressure work term, this is work done by the system due to pressure. Remember, the way that we calculate that is it's PDV work. Right? So it's integrating the pressure times a little bit of volume as we go from some initial volume to some final volume. If it's a rigid container, that means the volumes aren't changing. And so since the volume's not changing, then you have no pressure work. Okay? So that's what I mean by a rigid container. The volume doesn't change, so you don't have any pressure work. Another one that's pretty common is negligible change in kinetic and or potential energy. That might occur if you're dealing with a system that's stationary. If the system is moving around rapidly, changing its speed or moving elevation, then those assumptions might not be good ones. But if it's just a stationary system, or one that just moves very, very slowly so that the kinetic energy is always about the same, or only changes its elevation a very small amount so its potential energy is about the same, then it's a reasonable approximation to say that changes in kinetic energy and changes in potential energy are zero. Okay, so that's a pretty common one that we use. Another one that's specifically applicable to this form is if we're dealing with a steady state. Steady state is a very common assumption. It means that things are not changing with time. So you can see I've written here ddt of whatever. The three dots here just means whatever. So the time rate of change of whatever is zero. It means it's not changing with time. It always looks the same. And so if you were dealing with a steady state situation, then this term here, for example, time rate of change of total energy in our control volume would be zero. So that's a common assumption if you're dealing with things that aren't changing with time. Okay? Now there are, of course, other modeling assumptions, but these are some major ones that you'll see as you work through problems. Okay, one last thing before we end the video lecture. I just want to recap a good approach to problem solving. I think just a reminder of some things to include when you're working through problems. Number one, always identify your system or control volume. And you can do that with a dashed line. And be careful with that. Don't just draw kind of arbitrarily. You want to make sure that it's a relevant system or a relevant control volume. Just identify what it is we're analyzing. And you want to do that so it's clear to you as well as clear to everyone that's looking at your work what it is you're doing. Okay, so make sure you do that. Number 2 is draw an energy flow diagram. So draw where the heat transfer is coming in, draw where work is being done, you know, like in this picture here. The energy flow diagram is really just identifying the system and then drawing these arrows to identify where you have heat interactions and work interactions. All right, those will help you solve the problem as you go forward. And again, it's all part of the communications effort to explain to other people what it is you're doing. The third thing is write the fundamental relations relevant to the problem. What I mean by that is it the first law that's important for this problem? Is it conservation of mass? Is it the second law? Write the fundamental equations relevant to that particular problem. So if we were going to find how the temperature changes for something, that would be a first law problem. So what I would do if I was dealing with the system is I would write down, I'll just put for example here, I would write down my first law expression. Don't simplify it right here. Write it in its full form. Okay, so there's the first law in its full form for a system. Don't do any simplification yet. Simplification will come in the next set of steps. Okay, so write down your fundamental relations that are relevant to your particular problem, like the first law that I've written here. Now, this next step is identify significant assumptions. So these are going back to, for example, these assumptions I mentioned here. This will depend on the particular problem you're solving. You know, it depends on the geometry you're dealing with, what the situation is. But you want to identify significant assumptions. Is it a steady state problem? Is heat transfer important? Is it a rigid container? You want to identify those and write those down. And again, to communicate to others what it is you're assuming about that problem. Now, I always get the question of, you know, what assumptions do I have to write down? Do I have to write down every assumption? And the answer is, I'm going to give you kind of a waffly answer, but you want to write down the significant assumptions. The reason I say that is because we make a lot of assumptions all the time. For example, if you assume like gravitational acceleration is 9.81 meters per second squared, you're actually assuming that. It's not the same value everywhere on Earth. If you're near Mount Everest, the value for gravitational acceleration is a little bit larger than if you're somewhere else, like maybe, I don't know, in Death Valley. The number changes a little bit, right? It's not the same everywhere. But we've assumed that it's the same everywhere. But we don't write that down as an assumption because it's one that we all commonly accept. It would just be a whole lot of extra work to write that down. So, you know, there are little things you don't have to write down. The more major ones like adiabatic, steady state, rigid container, those kinds of things, those you want to write down. If you're in doubt, just write it down. It's better to err on the side of being conservative, where you write down more information than what you really need, than to leave information out. Okay? And then once you identify significant assumptions, the fifth step is to simplify the fundamental relations using the assumptions. So, for example, if I was dealing with a situation that was adiabatic, then I could set the Q equal to 0. And I would say it's 0 because of the assumption of adiabatic. It's an adiabatic process. Okay, so, and then once you're at this point, I won't write any more down, but once you're at this point, then you go into mathematics. You do some whatever manipulations you need to do to arrive at whatever expression you're looking for. Just do those mathematics in sufficient detail that someone can follow it, and it's easy for you to debug if you make mistakes and you need to go back and review your work. You just want to have enough information there that you can figure out what it was you did. And then when you get to whatever answer you're looking for, just make sure that you box it in or identify it clearly, and only write out 3 significant digits for your final answer. It's fine to put more significant digits along the way, but just for your final answers, use 3 significant digits. And then, if needed, interpret what that result means back into the real world. Is there some significance to the number that you found? If that's something that you need to include, just make sure you do that. All right, that's really all I want to say for this video lecture. A lot of the important content for this topic is actually in the example problems. So I have some video examples and text examples for you to take a look at online. Make sure you go through those. Try to work those out on your own first before just looking at the solutions. So you want to try them on your own. Don't just review the solutions and say that it all makes sense. Work them on blank pieces of paper. Okay, we'll end it there.